Okay, guys, so today we're going to go over 10.4 from your Briggs book. If you're not using Briggs, if you're using the Stewart book, this would be 10.3 and some change right around there. So overall, though, what we're going to talk about today is the integral test and the test for divergence. The test for divergence is basically the greatest test ever in this chapter because it will allow us to do very little work and figure out divergence, okay? However, there's something you have to remember. Okay, well, let me read it to you first, and then we'll talk about that. For a series, n equals 1 to infinity a sub n, if the limit of the sequence a sub n as n approaches infinity does not equal 0, then, then the series diverges. So this is very important to note. This is extremely important. All it says is if the limit of the sequence that we built the series from, if that limit is not 0, then the series diverges. Not the sequence, the series, because obviously the sequence can converge to like 7, and that's totally fine for a sequence. But for a series based on that sequence, if the sequence does not converge to 0 as you approach infinity, then the series that is generated from it is divergent. This is a one-way street. You cannot say, or I shouldn't say a one-way street, but the opposite isn't true. If it's not equal to 0, then it's convergent. No, that doesn't work. This is only a test for divergence. So the divergence test can only tell you divergence. It can't tell you convergence, okay? You might think that, well, if it's not divergent, then it must be convergent. That's not true. It just means the test doesn't work for that particular problem. So if we take a look at these, problems, it says determine if the following series are convergent or divergent. So right here, the first thing I do is I take the limit as n approaches infinity of n squared, and that's going to be infinity. So this is divergent. Oops. So, or you know what, let's write it like this. So this diverges by test for divergence, right? Okay, because equaling infinity is not equal to 0. Now this one, let's take the limit as n approaches infinity of 2n factorial over 2n plus 2. This is supposed to be a factorial, by the way. I just wrote it back. 2n plus 2 factorial. Well, that will be the limit as n approaches infinity. Remember, factorials, sometimes it helps to write them out. So let's see here. 2n times 2n minus 1 times 2n minus 2, so on and so on. This would be 2n plus 2 times 2n plus 1 times 2n times 2n minus 1, so on and so on. So all of these would cancel with all of those, and we would be left with 0. So this is inconclusive. So this would be inconclusive. Basically meaning we have to look at this a little bit further, right? Because remember, what we're saying is that this series, the sequence that builds it does converge to 0. The sequence converges to 0, but that doesn't tell us anything about the series per se. The series may still converge, or it may also diverge. We don't know. So whenever you get 0, that means you cannot use the test for divergence. Now this one, okay, let's see here. Negative n, so this is going to be the limit as n approaches infinity of negative n over 2n plus 5. Well, we know that that's negative 1/2, which is divergent by test for divergence, or divergence test. Right, so we know that this limit is not equal to 0. The moment you get a limit for your sequence that is not 0, you're done. You don't have to do anything else. You say that the series is divergent, okay? You guys understand that? So we're using the limit of the sequence to help us figure out the divergence or the divergence of a series. Remember, it only works for divergence for the divergence test, Okay, each test has its own little niche that we want to work with. This one only works on divergence. Now this one, this says the limit as n approaches infinity of 1 over n, well, that equals 0. Now you might say, oh, once again, it equals 0, so then it must converge. As it turns out, this is a very important series. This is called the harmonic. And the harmonic series, it's one of the first series that has or I guess one of the most basic series that has a limit of the sequence that equals 0, but it actually is a divergent sequence. Some sequences have a limit that equals 0 and their series is also convergent. Some sequences have a limit that equals 0 and their series is divergent. This is one of those first ones, one of the basic ones. So this is needs or inconclusive. We need another test for this guy, okay? So I want to take a look at this series, the harmonic. So this is the harmonic. So the harmonic series is a very special series. So we know that its limit equals 0, right? So what if I wanted to write out some partial sums? Because that's what we did in the very beginning, right? So I'm going to write out some partial sums for this series. So if I write S sub 1, you know, I get 1. If I write out S sub 2, I get 1 plus 1/2. If I write out S sub 3, or I'm sorry, S sub 4, I get 1 plus 1/2 plus 1/3 plus 1/4. And if I write out S sub 8, I would get that as well. So what I'd like to do, and again, if I was going to write this whole series out, this would, of 1 over n, this would be what, 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus so on and so on and so on, right? That's how it would look if we wanted to write, oops, it's kind of ugly. I guess I could write a little bit bigger. And that's how it would go on forever and ever, right? So we're going to take a look. We're going to take a look at these partial sums, okay? So what I'd like to do is I'd like to look at S sub 4 first, okay? And I'd like to kind of compare it to something else. So S sub 4 is the harmonic series, and we just plug in 1, 2, 3, and 4 for 1 over n, right? What if I replaced the 1/3 and the 1/4 with 1/4? Or I shouldn't say, let me just write this. 1 plus 1/2 plus 1/4 plus 1/4. Okay, so if I did that, which side would be bigger? Okay, this side would definitely be bigger. The left side would definitely be bigger than the right side because the right side has a 1/4 instead of a 1/3, so that's a smaller number. But we know that this side, 1 plus 1/2 plus 1/4 plus 1/4 is actually 2. We know that, okay? So we can say then that S sub 4 is greater than 2. We know that. Okay, that's a fact. Now, what if I did something similar for this one and I replaced all of everything else after the 1/4, or actually, let me do 1/3. I'm going to replace the 1/4 with, or the 1/3 and the 1/4. So let me show you what I'm going to do. I'm going to do 1/2 plus 1/4 plus 1/4, just like before. And now I'm going to replace these guys with 1/8. And you'll see why in a second. Okay, now that is actually equal to 2.5. If you add those fractions up, you get 2.5. And it's obvious, once again, that that side is greater than the left side is greater than the right side. So we now know that S sub 8 is greater than 2.5, okay? So I don't know if you guys noticed, but we could actually rewrite, sorry about that. We could rewrite this as, this is pretty big. So this is S sub 8 is greater than 2.5. I'm going to need all the room I can get. I didn't leave myself enough room. So we now know if we want to think about it, notice the powers that I'm working with here. Okay, the powers are 1, 2, 4, and 8. Those are all multiples, or those are all powers of 2. So I could rewrite this as s sub 2 to the k, right? All right, so, and again, k could be 0, so that's how we could get the first term, okay? So we know that this will always be bigger than 1 plus k over 2. We know this. This is for sure, right? Because what I'm doing here is, if you look at this and you look at this, the partial sums we're looking at are all powers of 2, and they will always be bigger than the first term, 1 plus k over 2. So in this case, k is 1, so greater than or equal to, let's say. Actually, I think it's strictly greater than if you start at 1. Yeah. Okay, so let's go strictly greater than for now. So that means that we can take the limit as k approaches infinity. You know what, let's do greater than or equal to, but then we'll have to get rid of it because you'll see the final value we're approaching. We're going to take the limit as k approaches infinity of s sub 2 to the k, and we're going to compare it to the limit as k approaches infinity of 1 plus k over 2, okay? Now we know that this value is going to be infinity. Now here's the thing. This is representing these guys, right? So this right here is representing this. This right here is still representing this. It just depends on what your k is, right? Okay. And this are the s sub 2 to the k, which is this guy, okay? So here's the thing, is we know for a fact that this is always bigger than this or equal to, right? So then this must be greater than or equal to 1 plus k over 2, but that equals infinity, okay? So here's the thing. Actually, I should probably put or equal to in here just to kind of clarify it. So s sub 2 to the k, as k approaches infinitely large, will be bigger than the right-hand side. But the right-hand side, limit as k approaches infinity of 1 plus k over 2, is approaching infinity, okay? So as k approaches infinity, the right-hand side approaches infinity. The left-hand side, which is the partial sums of 1 over n, the partial sums of the series 1 over n, is greater than that. So that means that the partial sums are greater than infinity, which means they're infinity themselves, right? So that means that this means that this sum must diverge because it's larger than that sum, okay? It's larger than that sum. So that guarantees us to diverge. And basically, this is something that somebody else had shown me a long time ago. And then this is also a lot of professors use this. If you're thinking to yourself, how would I have thought to do this to prove that? You know, I didn't know this when I first saw it either. That's why I'm showing you, is that this is some of the ways that mathematics works at higher levels is you're kind of asked to just come up with stuff. So you can't always just do what somebody tells you because nobody's going to tell you to do this. You have to think of it. And again, somebody had to come up with this in the first place. And what they did is they just compared partial sums. And obviously it was kind of nice that we replaced these with specific numbers that gave us nice clean numbers. Okay. But again, this isn't something you're going to have to reprove on the exam. This is just the idea behind the harmonic. We're going to find a much faster way to prove that a harmonic is divergent using the p-series. Okay. So what I'd like to do now is I'd like you guys to pause the video and determine if the following are convergent or divergent. If they're convergent, find the sum, okay? So we have these values here, all right? So pause the video and give these a shot. Okay, so hopefully you guys are back. What you should have done first with this one is you should have split it, and you would now have the series n equals 1 to infinity of 3 to the n minus 1 over 6 to the n minus 1, which you should recognize as a geometric, minus the series n equals 1 to infinity of 1 over 6 to the n minus 1, which you should also recognize as a geometric. So what we're going to do is we're going to say that this is actually 3 over 6, but we know 3 over 6 is 1/2, right? So this is really 1/2 n minus 1 minus 1 over 6 n minus 1, okay? And these start at n equals 1 to infinity, n equals 1 to infinity, okay? Now the thing is we know that this guy is convergent because 1/2 is less than 1, so convergent by geo. And we know this guy of 1/6, this geometric, is convergent because that's less than 1, and this is convergent by geometric, okay? So now what we can do is we can find their sums. So it says the first term, which in this case, if we start at 1, that would be 1/2 to the 0, which is 1. So this would be 1 over 1 minus r, which is 1/2, okay? Minus 1 over 1 minus 1/6. So this will become, let me see here. What is that, 3/2? 1 over 1, no. 1 divided by 1/2 minus 1 divided by 5/6. So this will become 2 minus 6/5, which will become, what, 4/5, I believe. Let me just double check that on my calculator. Yeah. Just wanted to make sure. I was pretty sure. Okay, so then that would be our sum. So remember, what we're using here is convergent, since the sum of two convergent series is also convergent. And we used a property in the previous sections that told us that the sum of two convergent series is just, you take those two sums and you add them up. Okay, so let's go over here now. So this one's a little bit harder. This one we have to, this is a telescoping, right? So this is going to be the series. If we clean this up, if we do PFD over here on the side, you guys, I'm assuming, will be able to do this. Let's see here. We're going to get 1 over n times n plus 1 equals a over n plus b over n plus 1. So this would become, if you do the PFD, you guys have to, go through and do it, but it's a pretty nice one. It's going to be 1 over n minus 1 over n plus 1. Okay, very similar to the one we did the other day in the video. So this is 1 over n minus 1 over n plus 1. By the way, this is why you cannot split up two series, and so you cannot do this. You cannot do that because this series is divergent. And so you would say that this whole thing diverges then, right? If you were thinking about it that way, and you would say, oh, because this one approaches infinity, then the whole thing, the sum of this must be divergent. You can't say that. You're not allowed to. You can only split up two series like that if they're both convergent series. So we can't do that. So what we do instead is we use the telescoping, okay? So what we're going to do is we're going to write out some terms. So plug in 1. This would be 1 minus 1/2. Plus 1/2 minus 1/3 plus 1/3 minus 1/4 plus 1/4 minus 1/5, so on and so on and so on, right? So let's see here. I stopped at n equals 1, n equals 2, n equals 3, n equals 4. So what's left standing So let's see what cancels. So this 1/2 cancels with this 1/2, this 1/3 cancels with this 1/3, this 1/4 and this 1/4 cancels. So what's left standing is this negative 1/5. Now, what is the relationship to the 1/5 to n equals 4? Wouldn't you guys agree that that's, you know, 4 plus 1, or in your notes, I think it might be k plus 1. So what we're going to do is we're going to say the limit as k approaches infinity. You know what, I'll leave it as n just to not cause any confusion, but normally they like to switch the notation. As n approaches infinity of, yeah, you know what, I got to switch it to k. So then we say the limit as k approaches infinity of 1 minus 1 over k plus 1 equals, I believe it's 1. 1. Yep. So that would be our sum convergent by telescoping. So you tell me how you know it's convergent. When you take a telescoping series and you get a sum, that sum is convergent. Now, if you ever take this limit right here and it's not a number, let's say it's not a finite number, let's say it's infinity, well, then you would say that this is divergent by telescoping, okay? So that happens sometimes. I've seen them, like I said, with natural logs and things like that. But this is pretty much a straightforward way to do that. So let's take a look at these next two problems. Okay, so this one, I already know what I'm going to use on this one. I'm going to take the limit as n approaches infinity of n plus 1 over 2n minus 3, and that equals 1/2, right? And that means divergent, because now, again, this is not what number? This is not equal to 0, so the divergence test applies. So divergent by test for divergence. Okay, and that's it. That's all there is to it. So the divergence test is the greatest one ever. Look at how hard these two were compared to the divergence test. So if you can take a look at a series and then see the sequence that's inside of it, inside the notation, if that sequence has a limit other than 0, you just say divergence by the divergence test. So this one, I want to try it again. Limit as n approaches infinity of e to the n over n squared. But that's infinity over infinity, right? So what I'm going to do is I'm going to use a L'Hopital's, and this will become the limit as n approaches infinity of e to the n over 2n. But that's still infinity over infinity, so I'm going to use another L'Hopital's, and this becomes the limit as n approaches infinity of e to the n over 2, which is equal to infinity, which is divergent because it's not equal to 0 by divergence test. So that's a pretty straightforward way you can use the divergence test, or you can use some of the other information we used, splitting two convergent series to find a convergent sum using the telescoping series. So now we have to talk about the integral test. So we're going to do this. This is a little explanation. So we're going to look first at 1 over n squared. And you could do a similar situation with 1 over n to show divergence. I'm only going to do one of them in this video. But again, this is just kind of an understanding. This is not a proof. This is just kind of understanding what's happening. So let's say we want to look at 1 over n squared and determine if it converges or diverges. So what I'd like to use is I'd like to use the limit. I'd like to use the integral of 1 over x squared dx from 1 to infinity. Okay, and notice whatever your starting point is here, that's the same as you use for your integral. And we want to use this to help us determine if the series 1 over n squared is convergent or divergent. So what we're going to do is I've taken a moment ahead of the class to write out some rectangles. Our old-fashioned way of finding area under a curve was using rectangles and then making an infinite amount of them. And the thing about a series is, if you remember that a Riemann sum, the limit of the Riemann sum at infinity is how it's kind of like the old-fashioned definition of a definite integral. So they should instantly be relatable to you in your mind. Whenever you see a series that's being added up, what's an integral? An integral is adding up areas. So it's a similar idea. So what I'd like to do is I drew rectangles with right endpoints, and I kind of graphed the side from 1 to infinity of f of x right here. And what I'd like to do is I'd like to find the heights of each of these rectangles and write some coordinates. So if this is the x coordinate of 1, the y coordinate would be 1, right? Let me just take a look at this real quick. So what I'm going to do, and then if I take and I look at 2, wouldn't this be 2 comma 1/4? And this would be 3 comma 1/9, and this would be 4 comma 1/16, right? And then this would be 5 comma 1/25, so on and so on and so on. I think you guys get the idea. So I want to show you something to compare this to, I guess. So if I took the series, let me write it way over here. If I took the series 1 over n squared, and I wrote out some terms, this would be 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared plus 1 over 5 squared. But wouldn't that just be 1 plus 1/4 plus 1/9 plus 1/16 plus 1/25? Right? That literally is the same exact values right here. Okay? Now, what are the areas of each of these rectangles, right? So this rectangle would have an area of, it has a length of 1 and it has a height of 1. So it would have an area of 1. What about this guy? This guy would have an area of 1 times 1/4. So this guy would be 1/4. This guy's area would be 1/9. This area would be 1/16, right? Because you're just multiplying by 1 because they all have a width of 1. And this area would be 1/25. So if I added up all of those areas, so add up my rectangles, well, the thing is we're starting at 1 and going to the right. So we're kind of stopping right here. So that other rectangle isn't even getting used. And what I know for a fact, okay, so if I add up my rectangles, I would have, you know, if we did include the first one, we'd have 1 plus 1/2. Sorry about that. Not 1/4, 1/9. Sorry, I was doing another problem. Well, if we were to add up those rectangles, we know that these would be all the rectangles after 1. So we kind of can't use that one. Okay, so here's the thing. What do we know about the relationship to these rectangles, which are, as it turns out, these values? What do we know for sure about these rectangles' area and the area under the curve of f of x, right? So if I'm going back to this now, if I'm going 1 over x squared from 1 to infinity, I know for a fact that all of these rectangles have an area that will be less than the area under the curve of 1 over x squared, because again, you guys can see it. We're missing this, we're missing this, we're missing this, we're missing some area. So I don't know exactly what the area is, but I know it's going to be smaller than the area of 1 over x squared. So what we need to do for these types of problems is we need to find out, we need to discover what the limit as b approaches infinity of the integral of 1 to b of 1 over x squared dx is worth. So we're going to take this, and this is going to become what? The limit as b approaches infinity of, what would that be? -1 over x, right? Because it's x to the -2. We add 1 to the power from 1 to b, right? So then this becomes the limit as b approaches infinity of -1 over b plus 1 over 1, which equals 1. So here's the thing. This is a finite number and is larger than the sum of the series, or larger than, well, than the sum of all the terms of the series, or larger than the series n equals 1 to infinity of 1 over n squared. So the thing is that we know that this is in fact, n equals 1. We know it's smaller than that. Now that's again not including, we're not including this first term right here, right? Because we're only going from 1 to infinity, so the area right here to the right, we're saying all of that area to the right has to be smaller than 1. If you include the rectangle, then it technically would have to be smaller than 2, which is, I think it was Euler discovered that it was pi squared over 6 for this actual series right here. So Euler discovered, I'm pretty sure it was Euler, that this ends up being, I believe it's pi squared over 6, if my memory serves me. Now, again, in general, we're not supposed to know that. We just know that it's finite. It's smaller than a finite number. And these terms from 1 and on, all of these rectangles area must be smaller. So that means that the series after 1 has to be smaller than 1. Okay, that's a guarantee. So by doing that, we can compare them and say, well, if this one's convergent and or if this one's a finite number and the other one's smaller than it, then that one must also be convergent because it's smaller than a finite number. So that's how the integral test kind of makes sense. But there's a couple stipulations that you need in order to use the convergence test. I'm sorry, not the convergence test, the integral test. So the integral test says, suppose that f of x is a positive continuous decreasing function on the interval 1 to infinity, and let f of n equal a sub n. Then these three things must be true. Or then this is what you can use. If the integral of f of x dx is divergent from 1 to infinity, and it doesn't have to start at 1, that's just where I started it for these, then the series a sub n is also divergent. If the integral from 1 to infinity f of x dx is convergent, then the series is also convergent. Something that's important to note, the integral test does not actually tell us the sum, what the sum converges to. It only tells us that it does converge or diverge, okay? So the integral test doesn't actually tell you the value. It only can tell you convergent or divergent of the series. You may know that the integral converges to a value, but that doesn't tell you about the series itself. And also just a note, the series does not have to start at 1 for the integral test to be used. Sometimes we have to adjust our starting points because f of x is not decreasing for 1 to infinity. So sometimes you might have started at 5 or e, or not e, I'm sorry, like at 3 or something like that. Okay. So let's do this one together. So it says, does the integral, or does the series 1 over n squared plus 1 converge or diverge? So first off, we know that it is, we could graph it and we could see that the f of x equals 1 over x squared plus 1 is a positive, continuous, and decreasing. In general, you just have to write these to show me that this is the integral test applies. So we now know that these three things are telling us that we can use the integral test. And then we're going to take the limit, or we're going to take the integral from 1 to infinity of dx over 1 plus x squared equals the limit as b approaches infinity of dx over 1 plus x squared. But this should look familiar to you. You guys should know that this is tan inverse of x, right? Oops, sorry about that. The limit as b approaches infinity of tan inverse of x from 1 to b. So now let's take a look at this one. So that means that we're going to have the limit as b approaches infinity of tan inverse of b minus tan inverse of 1. Well, let's see here. What is the tangent inverse as b approaches infinity? So if you graph tan inverse on your calculator, which is a good way to do this problem, you should do y equals, oops, I got to change my mode. Okay. So let's go to y equals, and I'm going to do tan inverse of x. Okay, I'm going to graph it. So as b approaches infinity, let's go to 10. Oops, window, let's go to y max of, let's do pi halves. So I know that as you start approaching infinity, of the arctan, remember that arctangent, arccosine, and arcsine take on the range for their domain and the domain for their range of the original functions. So that means that we are approaching, as we approach infinity, pi halves, which used to be the asymptotes of original tangent, okay? So now, and then the arctan of 1, well, that would be pi fourths, right? Because what angle would create a tangent, or tangent of theta would equal 1? Well, that would be pi fourths, right? 45 degrees. So that means that we actually get pi halves minus pi fourths is pi fourths. So we now know that this is a convergent sum. So the series 1 over n squared plus 1 must converge by integral test. Because this was a convergent sum, then the series must be convergent. That's what this is telling you up here. That's what this is telling you right here. If the integral of f of x is convergent, then the series of a sub n must also converge, okay? So let's take a look at this one. So this is a little bit more difficult one. So it says, does n equals, or the series n equals, sorry, n e to the negative n converge or diverge, okay? So we're gonna double check if it's positive and continuous and decreasing. In general, the only thing, or the only hard one normally to check is decreasing. So I went through and did a derivative on this one. Remember from calculus 1, the derivative can tell you if something's increasing or decreasing. So it says find f prime, or I'm sorry, f of x from 3 to infinity is obviously positive because you plug positive numbers into n or e to the negative n, you're always going to get positive. It's obviously continuous because there's no way this can ever be 0. There's no asymptotes, vertical asymptotes, I should say. And then decreasing, pretty sure, but I'm going to double check. Normally decreasing is the one you have to check. So I find the derivative, and you see my work here, and I make my little sign chart, and it shows that it's negative after 1, meaning that the function is decreasing after 1 because its derivative is negative. So we know that it's decreasing for x greater than 1. And we're on 3 to infinity, so you know this is definitely greater than 1, so we're good. So check, right? So check, check, check. All 3 of these apply, or all 3 of these work. So then what we're allowed to say is that the integral test applies. So now, in order to do this, I have to do the limit as b approaches infinity of 3 to b of x e to the x. So I'm right here now. But this is a integration by parts. So I set up my integration by parts. And then this will be limit. Let me get to make sure I'm doing all this correctly. So we have limit as b approaches infinity of negative x e to the negative x. And this would be what, minus, let's see here, e to the negative x from 3 to b. That should be good, yeah. Ooh, wait a minute. I think this is plus. I think I made a mistake right here. Let me start over from right there, you guys. So this is u times v, right, minus integral v du. So we have minus the integral of v, but v is negative, so that's positive. So that's how I got that, yeah. So that's positive integral of v du. Okay, so now this will become the limit as b approaches infinity of, and again, this one's probably, I should write this 1 to b plus. Now, if I integrate this again, I'm going to get that negative x from the u sub once again. So this will be minus e to the negative x. And now all of this is from 1 to b. Let me make some room over here. So this will be the limit as b approaches infinity of, let's see here, of negative b e to the negative b minus e. You know what? I should factor this out, actually. Maybe make my life a little bit easier. Negative e to the negative x. And this would be x minus plus 1 from 1 to b. Maybe I can clean this up a little bit better. So this will be the limit as b approaches infinity of negative 1 over e to the b. You know what? I see a mistake in there. I got to go back and fix it. Let me just write this again. Sorry about that, you guys. So this will be negative b e to the negative b minus e to the negative b, okay? Minus, I guess it was a mistake. It was just I didn't like the way I had it written. Minus negative 1 e to the negative 1 minus e to the negative 1, okay? So now, when we plug our limit in, this will become the limit as b approaches infinity of negative b over e to the b, which is problematic. This will become minus limit as b approaches infinity of 1 over e to the b. That's no problem. And this will become minus the limit of this. There's no b to plug in, so this will just be negative 1 over e minus 1 over e. Now this one needs L'Hopital's, and this will become the limit as b approaches infinity of negative 1 over e to the b. This will become 0. This will become minus, plus 2 over e. This will become 0 as well, so we're left with 2 over e, I believe. Yep, which is convergent. So this is convergent. Let me do this real quick, you guys. I need some extra room. So then we get to say the series n e to the negative n from n equals 3 to infinity converges by integral test. Since this was convergent, the limit of this integral was convergent, then that means that the series is also convergent because it was positive, continuous, and decreasing. So really quick, I just have a few more minutes. One thing I want to kind of talk to you guys about is the P-test for series, okay? So this is like your favorite problem ever. The P-test for series says the series 1 over n to the p converges if p is greater than 1 and diverges for p less than or equal to 1. For our class, your series must be in this exact form as above. I mean, you can mess with the n equals 1. It could be n equals 3 or 4, but it has to be 1 over n to the p. You may not use the P-test for 1 over n to the p plus c or 1 over n to the p minus c square rooted, et cetera, so on and so on. I think this particular book, if you're using the Stewart book, they won't allow it, but in the Briggs book, I think they ask you to use the P-series for these. Please do not. You must use the comparison series, a comparison test, or something else, sometimes the integral test. So that's just something to keep in mind. and let's see here, what else do I have? Let me see. Do I have another one I want to do? I'm starting to run out of time. I gotta start my next class. But for this, you could go back and look at the harmonic. So if we have the harmonic, right? The harmonic is n equals 1 to infinity. We could say that this is divergent by Ptest since p equals 1. And it says right here, this is 1 over n to the p. It says if p is less than or equal to 1, it is automatically divergent. So that means if I gave you the series 1 over n to the 5th, n equals 1 to infinity, this is convergent by Ptest since p equals 5. And that's all you would have to do. You don't actually know what it converges to, but you do know that it is convergent, okay? I think in class, we will go ahead and use, I'll go ahead and give you a couple practice problems for some integral tests. But for now, that's going to do it for this video. Hopefully this gets you guys started on the integral test. Remember, you always have to check if those three things are true: positive, continuous, and decreasing. Let's say that it's decreasing after 7. Well, then you just start your series. You change your series from 1 to infinity, from 7 to infinity. Because by doing that, the previous 6 partial sums will be, or if you add up the previous 6 terms, those are obviously finite. So as long as you can prove that to infinity, from any number to infinity is finite, well, the previous terms are finite. So finite plus finite is finite. And remember, you're trying to prove convergence or divergence. And if you can prove that it's a finite sum, then you've proved convergence. You don't actually have to prove what the sum is. You just have to prove that it is a finite number. So that'll do it for this, you guys. I just wanted to kind of give you a nice little video on this. It's a little bit longer than I wanted, but hopefully it gets you guys started. Thanks for watching, and I'm going to post this in a little bit.